So, this is my last class. The next two classes is yours, right? I mean, this is my last one. I mean, full class, but we talk next class. We talk still do something, but this class will be basically my full class. Next two will be your presentation and exam. Right. So, just let you know that since some of you have been asking a lot of time that what might be the exam question looks like, so I, based on what I do in the previous years, I compile a sample questions that you might take a look. Okay, it will be very similar to, in terms of format, what you will see in the 2 weeks later, right? So we will be first page with this, and then will be some multiple choice questions. Sorry. And then some non-questions. So here I make the question like regression. You look regression, look at the results, and I ask you some interpretation, how to use it. And after that, I ask linear regression. I give the result and how to interpret that. Right? As you can see, as the punishment alpha lambda increase, then actually everything shrinks. So this is how you can take a look. I think that would be, useful for own learning as well. The very last question would be somewhat related to the A/B testing we'll cover today. Okay. Of course, as I said, this is a sample question. It's not indicative of what I may or may not exam, but you will see the style I'm giving. So this is the style is the idea. The long question will be I give the code, I give you the result, and then I ask you how to interpret that. So no need to worry about the code. The code already asked in your assignment already. So I'm not intended to ask anything about the code, except maybe you reading the code and understand what's going on over there, right? So basically, I give the code, and then the code result, and then you answer based on the code. Okay. I will not answer any question related to this sample question. I think actually, if you try to do it, copy and paste on the AI, probably you will get the answer already. So I'm not interested in answering question on that, but you should be able to see the thing from your assignment. Sorry, from your slides. If your question, neither TA or I will answer that. Okay? Because of for fairness, I worry about you just bring this to the exam theater. That would be not doing the right thing. So just figure that out yourself. So the second thing would be we will finish this lesson 6 today, and then we'll go to lesson 7. Okay, lesson 6 we just left several slides. We'll go over that. And then today we cover something what we call the causal analysis. Although I have 3 more slides to go, but I can't really do it. Probably I would do just lesson 7. I'm not even able to complete everything there. Probably I would just little bit skip over stuff, but later you will see what I cover and not cover. Okay. So the exam is up to lesson 7. Okay. That would be the thing. 8 or 9 or 10 will be sorry, I can't really cover that. Although I told some of your classmates I actually spent a month to prepare the new slides, but unable to cover that. What a pity. But anyway, we can just do whatever we have. Okay. So just remember, next class we have a quiz 6. Sorry, another quiz, and then we have a presentation as well. Okay. Presentation is next week, right? Presentation and the quiz 6. Okay. Quiz 6. Next quiz. Okay. Quiz will be the lesson 5 and 6 for the next quiz. Just multiple choice question. Okay. And I look at the result of the quiz so far. Everyone got full marks for all the quiz so far. So I'm expecting the same, right? Continue to everyone get the full marks for the next quiz for those who have done it. Okay. I saw 1 or 2 people haven't do the quiz, but I can't do anything on that. Okay. So without further ado, let me continue lesson 6. I know that many of you are getting more busy, so I just try to be going not too fast, but review what we have done. Okay. So this is the prediction and LISO. Okay. And to evaluate, there are many ways to estimate to evaluate how your performance of model. The main thing is the square function. And this is how you run a regression, right? You minimize the distance between your prediction and your outcome, right? And there's another thing you can calculate. And we go over this car data, okay? And tell you that what kind of model you should use, okay? And not going to do a lot, but important thing is when you want to pick different models, especially you see which type of regressor you want to use. When you actually care about prediction, then you use this to pick, right? But if you don't care about prediction, you should use the method we use in topic 5 and 4. Look at the star, whether they have star or not. Okay. If they don't have star, you forget about it. Okay. And there's difference between prediction and interpretation, right? When regression, you don't have stars, then they are not different from 0, then they should not be taken down into a model seriously. But when you do prediction, you don't really care about the model explanation by itself, in terms of prediction only. So you may still keep the regressor have no star. Doesn't really matter, because at the end of the day, you predict. You don't want to explain anything. Okay. So that would be the idea. That's why you use the cost validation approach to pick the right model. Okay. I hope I answer a question. So prediction. And some of you, I think, asked me after class and how you should approach your project, right? What's a framework? If you do prediction, that will be your framework, right? So you will be starting a problem, how to change the X and Y, and have a loss function, and a different model is let you predict, right? And at the end, you try to see is it good or not, right? And if you're not interested in prediction, you insert in correlation study, then the thing is, you don't have this, right? You just want ORS, right? The loss function is a square, and you also build different model, and then but you don't do prediction, right? You do hypothesis testing. You see whether the star are there or not there, and then that's the end of the story. So that would be the difference between when you are not interested in prediction, but rather you want to discover how they're related. Okay, so that would be things that we're different. So this will be the framework that underline your paper, the project. And many of you also talk about how large is the sample size that you needed, right? I mean, it's depend on the study you want, but at least I would say at least 50 samples, 30 to 50 sample size, right? But likely when you do business, then, right, more than 100 or thousands even should be something in your target range. But of course, depend on how expensive you generate data, right? Say for medical study, usually they would be having 20 something is already very large, right? Because you have a patient, you do a surgery, then already 20 something is very expensive already, right? But if you have a questionnaire, right, ask people, take, then I don't think where you just ask 20 people would be good enough. Or ask people to online survey, you would expect you to do more. Okay. So, but that would be the idea behind what is large enough sample size or not. Okay. And I guess there's a feature engineering. This is something we have covered already. And important is this LISO, right? And LISO is something if you learn statistics is like, it's very popular in the 10 years ago, right? But now, of course, now people, I mean, will use the method you use in learning other class, right? You use a complicated machine learning method, right? You have to, I know, probably learn some random forest and regression tree or other double descending or greatest descending, gradient descending, or other method that would help you better. But this is I mean, still there's some research going on this LISO. Okay, and just the definition is LISO is trying to punish when you have some positive negative coefficient, size coefficient, right? You get remember regression, right? If you deviate, have some slope, then you have some punishment. So I really don't want to have slope unless necessary, right? So that's how the LISO idea works, right? You look at the parameter alpha is this, right? It means that absolute value means positive, negative, you would punish. And adding all this means that every coefficient you punish at the same time by alpha. So if you want to run this regression, you want to minimize this loss, the prediction error, but also you want to make sure that the coefficient of the slope, right, to be as small as possible. Whenever you can make it zero, you make it zero, right? So that means that you try to automatically make it as small as possible. And that is turned out to be, this simple thing actually turned out to be very powerful in terms of selecting coefficients, right? And then if you remember the example we did, right? We have 320 something coefficient. And if you do appropriate LISO, and it turned out that we cut to 70 or 80, okay? And that makes our life easier, right? Because you can imagine for prediction, that's okay, right? That's you can have a lot of features that interact each other, and then that can be a lot, okay? So that is very helpful, okay? Let's go back to the example application, then probably we would guide you that way to. But one last thing to mention is that when you run LISO, you have to standardize your data, right? The reason is because of when you regression, if you double the x, the beta will halve the size, okay? That means that you don't want this sensitive to the unit, right? So that means that to be fair to each observation, don't want to scale. So we scale everything so that to 0.1, so that when you minimize, it's equal for each dimension. Okay, so that's why we have in this particular approach, you take different from the mean and over the SD. So that is but don't worry, this is in Python, it just automatically, we say the standard scalar, and you do it and use fit transform. This will give you the result directly. Okay, so this two line will do the job we want to. Okay, and as you can see in this LISO, you will just basically force the coefficient of the other become zero, and only keep the one that we still need to keep. Okay, of course, there's some drawback of doing it, is because of the regression may not fit very nicely, right? Because you just force the model to be simple. If the model is very complicated, in fact, you force it simple, actually you are underfitting, right? But that is life. You don't know whether overfit, right? So the only judge is use the LISO, use cost validation to check. So you never know you overfit, underfit. So and we mentioned about how to get the alpha, right? And in general, you can't really tell, but in general approach, but the machine learning idea would be use cost validation to train. Okay, basically use different alphas and do different cost validation, right? And you figure out which alpha actually minimize the cost validation error, right? Then that's how you do it. Okay. Just remember this example, probably it's good to go over again. So I have a data on Airbnb, Panda Lambda, download data. I mean, we know very well. And there's a lot of data we drop. Okay, you drop the data, a lot of cleaning. I'm not going to go over the this field in middle. I'm not going to go over the detail, but and then you look at this and figure out, you do the box plot, figure out the different room types different. So that's why you have different rooms. Okay. So that is some of you ask me why you need to do EDA, because of a lot of data, and data probably have different category, right? Your data is in this way, different room have different category. And the question is, should you include different rooms as a variable, right? And the easiest thing to do is you just plot a scatter plot like this by different group, and you see they're different enough so that different type of the room should be in your regression, right? Because that is, of course, not fully machine learning, right? You have to decide yourself, because LISO, you still have to choose what should be there, and the machine pick what within this thing you want to pick, right? You have to pick what's the biggest universe, but the machine only pick what is inside, right? The machine cannot tell what should be the bag you want to put in, right? The machine only tell you what to pick up from the box. Okay, you have to decide what to put in the box. So this is, you decide what to put in the box. Okay. And similarly, very often we will see sorry. They're what we call the interaction term, right? Say for this, right? Whether it's family, kids friendly or not, right? Will affect the price, especially look at the entire apartment, right? So this is significantly different from this one. You may ask, what is this thing means? This is an interval estimate. So this I don't know how to say, it's arrow, right? And this means these two are significantly different, because this range and this range doesn't overlap. Okay. If this range doesn't overlap, that means that they are unrelated. So in this case, right, cancellation policy actually will be different when you have kid or don't have kid, right? Because when you have kid, then might likely that you would likely to cancel, then you're on single person, you go, right? You have more flexible time. So you will see the different impact. So cancellation policy, of course, would more flexible, of course, we charge more, but actually the impact is likely to differ according to whether kids friendly or not, right? So that means that you would have the interaction term, you have the cancellation policy, kids friendly, and cancellation policy times kids friendly. Okay, so that's the reason why you need interaction. Okay, and similarly here you will see number of people and the price are kind of nonlinear, and there are enough difference, so you really want to do something. Okay, and that's why they have this type of regression, right? Explain why you want to do all this stuff. Okay, and at the end of the day, right, you will see number of variable we have 70, but if you allow interaction, you have 315. Okay, and if you remember what's interaction, right, means that they are not independent, right? So the joint effect is different. Okay, so that means that, say, suppose the example we have here is say cancellation process and kids friendly, right? The house which is have cancellation policy flexible, of course, charge higher price. Okay, and kids friendly house also charge higher price. Okay, but If the house is kids-friendly and flexible, can charge way much more. Okay, that's the interaction. Okay. And so here we use the cost relative method. Is FIFO. It's like you keep 20% each time. And this data, I hope you can start to look at it because it's in your assignment, right? So that is how you do the training test split. And then here we have OS validation, okay? And the same here, I'm not going to repeat, but you just looping over all the regression and calculate the RMSE. So there's a typo here. There's a space should be, there should be no space here. Okay. And then for each regression, okay, you would split, right? You would do 5-fold validation. For each flow, you will just run the regress, run the data based on the trained data. You calculate the RMSE based on text data. Okay. So that is something not too much worry, because if you run this thing, you don't, all the code are the same, right? There's nothing you need to modify this code, right? The only thing you need to modify is probably just the data, right? There's nothing I don't think you would change any of this code, right? But you probably want to understand each line, what they're meaning, right? Of course, I'm not asking in your exam, but your assignment, you should know what you're writing, right? It's really copy and paste is not good for you. I mean, at least you know what's going on there, or at least you can ask AI what's going on, right? Or you can ask me as well. I think I can try to help you, but AI would be very patient teacher to teach you infinite many times as you want, right? I mean, I think I'm patient, but I'm not as patient as the AI. So you can calculate the RMSE, right? So that's what you get, right? So this is run without LISO. Okay, this is 7 model, right? And based on the test RMSE, you pick the lowest one, then probably you pick this guy. Model 6. Okay. And if you do the BIC, and then probably you pick this guy, right? Model 3, right? R square, of course, you pick the biggest one. And you actually will see this type of model, the train RMSE is dropping, and this is go down and go up, actually reflect overfitting, right? You fit the more complicated model, you fit a lot of the feature that is not exist in the data, okay? Because that may be the only feature in the train data, not the test data, okay? So that's why you would have this thing happen. And here, we want to say the biggest model have 315 parameter, and many of them may be redundant. Okay, so if you drop them, actually you can do a better prediction. Okay? So that's why LISO is very powerful, because I can build the model as big as possible, okay, and make a LISO to do prediction. Okay, then you'll be great. Okay, but I want to remind you that when you do prediction, don't try to put as many as possible. You only put something is relevant. Why? I think we see this Twitter post maybe last week. I mean, after the class, I go home and I saw a picture of a running time series data on ice cream sales and shark attack. Okay, and you can imagine that the days with more ice cream sales would have more shark attack. So if you do a prediction, it's ridiculous, right? You will say the day with more ice cream, then you have more shark attack, because the ice cream attract sharks, right? If you think that's true. But of course, behind is what? Because of more ice cream is because of is beach. People go to more beach, it's sunny days, right? And you go to the beach, and then more likely you get attacked by sharks, right? So if you forget about this link, then you do the prediction, and then of course you get a ridiculous, very greatest fit model you can get, but likely that your model will be rubbish. I mean, of course you do a prediction, but it's nothing you'll be anything useful. So you should also exercise care what should be in the universe of the regression. Okay. So here's the test training split there. And just to remind you, because the way the LISO is being done, you have to use a very special, I don't know why they do it, but anyway, you have to do this. It's a special function called Ph.D. Basically, you have to separate X and Y in terms of matrices. And then once you do that, and then you have to, once you do that, actually, they will convert into a some kind of matrices, okay? D got D matrices, design matrices, and then you have to do the splitting, okay? Of course, in you run the regression, in your case, you basically just only change these two things and maybe change this one. Other than that, you just copy the code I have. So if you worry about things, you can just copy the code, okay? And then you scale the model because I run the LISO, right? So that's why I scale it. And here is the thing that have to be careful, but probably I didn't mention careful enough last time is I rescale the data based on the trained data. Okay, look at trained data. I scale it by taking the mean of the trained data for each one and over the SD of each one, right? To be fair, when I scale the test data, I subtract the mean based on what I have done. Okay, so I use the mean of the trained data to do the subtraction. Okay, I'm not standardized based on the test data. Okay, I use the mean from the trained data to do the subtraction. Is that clear what I'm saying? If not, then maybe this. So you'll be doing this in case you don't see what I'm saying. So the data is a lot, right? This is a whole data set. And here you have 20% is your test data, right? And 80% is trained data. Okay. So for each variable, say variable x1 and blah, 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 right? And the first variable, how you standardize it, you take the mean of this, and then you take each variable, subtract the mean, right? And over the SD of this, right? And that's how we standardize the trained data. But how we standardize the test data? Are you going to subtract the mean its own and divide the SD? No. You will use the mean of this for subtraction. Use the SD of it to do subtraction. So that is how we standardize, right? Because that is how you actually do in practice, right? You have standardization through this, to be fair. You minus the mean of this stuff and divide the standard of this one. So that's why in the code I have is the first one, fit transform. I fit it. And then based on that, I transform. I just do the same again. Okay, so that's to say is slightly a little bit tricky, but of course, look at many textbooks say they were that already, but I just explain why you want to do that. Just for fair comparison. And here would be how we do the LISO. I make the alpha very big here so that I can have a shorter result. Okay, probably you should use a smaller alpha. Okay, and here is I run the alpha and I define the non-null LISO by rounding the coefficient to two decimal places. If I round the decimal place 0, then I consider 0. Okay. Then I show the result. right? That would be your model, right? So that would be very simple, right? If I have alpha 4 is very large, so that's why actually I cut everything, only left 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So only left with 13, right? We start with 315. And if alpha equal to 4, you only left with 13. So very few. Of course, if you set alpha equal to 0, then again you get 300 coefficient. And then you set more, then it will be reduce the number. So that's LISO is very powerful. And of course, you can calculate the RMSE there. Okay. And here I didn't pick the best alpha. Okay. So how to pick the best alpha? As I said, you do 5-fold validation, right? So for different alphas, I do a cost validation, and I check for every alpha which one gives the lowest. Then that's the thing I do. And fortunately, LISO has an automatic feature. You don't have to do it by yourself. You don't have to code it. Already someone code it for you. It's called LISO CV. So that's why Python makes our life very easy. Okay. And you just tell what kind of alpha you like. Okay. And then you tell the model, I want LISO CV. What's the list of alpha I want? How many fold of validation? And this random, whatever number you want, and you fit it. Okay. And there's some reason why you have to raffle here because of this is a matrix, but you only want a vector here list, so that's why you do this, and then they collapse the matrix into the vector. So that's something that due to the reason of the data type. And once you do this, you will drop to 300 to 70 variables. And the interesting thing is, perhaps surprisingly, you reduce the number of coefficient. The RMSE actually dropped by 10%. So smaller is beautiful, right? Not bigger is better, right? So, and then that would be the idea, okay? And also there's a idea is if you don't know what to pick, okay? When you do prediction, the recommendation is to use a simpler model. And because of very complicated model, actually usually doesn't work very well, okay? Unless a lot of data. And this is we go through last time if you run through the coefficient there. Okay. This is how you do it. You took the data, call it data frame, and you figure out you take 3 coefficient not equal to 0, and this is a list of the coefficient. And that's what I said. There are 71 coefficient. And what I do is look at the top 10 list there, and I reindex them, look at the coefficient, look at the absolute value. So I don't care about small and large. And I look at the n largest of the top 10. I get the index. Why I got that? When I got the index, I can take them out. So that would be I just plot it. That is very standard plotting. The only new thing is that AXV line, which to say at 0, I have a line there. So if you forget about that, it's okay. This is new there. Okay. This new there is just drawing this dotted line. Okay. And another new is the grid axis X. So this would give you this X. Others you have seen already, right? Like this line, horizontal bar, X label, title, total bar. Okay. So there's nothing new there. Okay. And this is the code that you want to look at all possible RMSE in every false because you have five-fold validation, right? So that means that you would try to look at different lambda, and this is the result, right? And probably you are not interested in this by itself. You want to pick the best one, right? So you pick the very best one. This will be 0.7. So in this particular model, alpha set to 0.7 is the best, okay? And why best is just trained to be lowest. The RMSE is dropped to 37.98 or like 48, okay? Now here comes to the very last part, which I don't have time to cover. Now I cover this last two slides, then we're done, then you are ready for the next quiz. So here is very often we will plot a y hat plot or y hat y plot, okay? So you may be it can be very confusing because the textbook sometimes they plot the y hat plot, sometimes the y hat y plot, then I'm also confused. But doesn't really matter you plot, but that have to be very careful what you're looking at. So so here I have the y hat plot. Okay. So what do you mean by y hat plot? So so basically first you put a scatter plot and over the test and prediction. Let me show a picture for you there. So this is what, okay? And this 45-degree line is when y hat and the y are the same. So if your model is perfect, every dot should be on the 45-degree line. Okay? But since you're not, that means that your data doesn't predict that well, right? And you can look at this case, okay? Suppose this number, okay? This data, according to your model, okay? This should be, the price should be here, right? The price should be this number, okay? But you just maybe 300 something, right? And actually they charge you 500. What does that mean? This is overcharging you, right? So what does that mean? It means that the thing that above the 45-degree line is actually overcharging, right? Remember, the rule of this is I want to pick the best deal, right? Airbnb, right? So I want to look at, in this model, I'll look at the data actually is below the line. The lowest below is the best, okay? So what's the best deal here? Possibly maybe this one or this one, okay? Depends on what you think. But this probably is a good one because suppose they should charge you 180, but you are paying that like $80. So this is a good deal, okay? You shouldn't miss, okay? Either you miss something, maybe there's some murder happened, it's not in data, right? But or there's something crazy going on, but otherwise if nothing crazy, then this is something you should go for it. Okay? Maybe too good to be true, but you can check, right? So this is how you would use this kind of YY hat plot to visualize what is the model, right? Also look at how good fit is this data as well. Because looking to this is, if everything is not nice, especially here, means that your data is here. So it means that your model actually works very well when the price is between 0 and 200. And if beyond, actually your model is either under predict or actually they are overcharging. Right? So either there are two ways to do it is either you should change the model for higher prices, or they require different type of model, or you just use the model in this normal ranges. So this is usually what we call the after prediction diagnosis, right? So you look at how your model performs and see whether you can improve it. Okay, just to repeat, if the moral of this story would be, one, if you want to find a good deal, you'll be here. If you want to find who is the worst guy overcharge you, maybe somewhere here. Right? And here, all these points are very close to the 45-degree line, that means that you would trust a lot of your model when data within this region. And this is a little bit over there. You should have less trust over this area. And third will be, it seems like the model is under predict, okay, when the price is high. So you should try to check whether you want to change the model or you want to separate the model into two different parts. Cheaper prices is here, more expensive to go into other type of model. Okay, so that would be the how I would suggest you do this. Okay. And here is at the end, I just combine the result with our regression. Okay. This is basically the first 7 lines is coming from what we have done. And LISO is the thing we provide. And you see, actually LISO, not surprisingly, our best fit model, of course, beating every single model that you can imagine. Okay. So that's why LISO is very popular in terms of prediction. Okay. Do remind yourself that it doesn't say this a bad model. Okay. It just say if you use prediction, LISO is good. But maybe LISO is saying something nonsense model, right? And you can't explain very well. Okay. If you really want to explain your model, has some business prediction, so it predicts actionable advice, you would still use this model, right? Because the coefficient, if they have passed through the hypothesis testing, have 3 star there, you can say something, right? If there's some star there, suppose maybe cancellation policy can increase price a lot, okay? And maybe the suggestion is doable, actionable business decision you can do, right? But when you LISO, when you see the LISO coefficient is you still keep there, doesn't mean anything, right? It's just basically this is the best predictor, but doesn't mean that you change this or increase this and help you to increase the price, okay? Because only prediction, okay? So because prediction can go one way or the other, so the coefficient doesn't say anything too much. But so that would be the moral of this. Is there a question? Any question? So we're basically done with our prediction or regression stuff. So we go to the third part of the class. Only lasts for 2 hours. Sorry, less than 2 hours. But it will be the next after the break. What we're going to cover is always said we will do causal analysis on random experiment. Okay, and let's have a 15 minutes break, and we do a UE apply.
我已經係 cut 咗㗎啦，你呢個打開咁啊。More or less the same style. More or less the same style. Not the same question. The same style. Yeah, there's something I can do this. Formulation, prediction. What's exactly?睇你寫出嚟。你如果覺得你俾個拉人，你俾你個 boss 我係個 report 啫，係你着衫喎。
So maybe we can continue. So let's see your result. Do we need to do prediction? Need not be, because you may just run regression as a correlation exercise and test hypothesis and do some prediction, and that can be done, right? Because it really depends on the goal of your model, right? If you really care about prediction, and that your prediction, right? And how many model? If you run correlation, maybe just need one model, right? Or maybe more than one model, simple model, more complicated model, right? You can do that. And there's no number you need to, but if you present, I guess you present the best model, right? You don't want to present, I have 5 model and this is my model, right? You probably present this the best model and what you get, right? So remember, you are presenting your main result. You don't need to tell me how you arrive your answer, at least in the presentation, right? And you tell me the main core of it, right? You don't, at least you already present to your client or your boss, right? You don't really need to tell how you discover this, right? You just tell me the final answer, right? You want to predict this. These are all the good predictor. You want to look at how Y and X correlated, and these are most important thing. And here's how I discovered, right? So focus on the question, right? Focus on what you should do, right? Deadline assignment. I think do you need extension for this? Okay, extend. Yeah, that's fine. So it will be 21st. You can submit. Yeah, that's fine. Very last class. I cannot further delay because I need to submit your grade in December 2nd. So I just have only 2 weeks to grade everything. So cannot be too delayed. I mean, I submit the grade doesn't mean you know the grade, right? So have to wait. And so let me change the I guess you change the assignment, right? So I think it's 21st. 21st, right? It's 21st, I guess. So I change it to 21st. Next question. My question is, I don't know what my question is. I think it's very good because you know what you don't know. something is already very good. And that's actually, you're better than most of the PhD, because the PhD is, when I do doctoral degrees, you know what you don't know. And you're already at your master level, you know what you don't know already. I congratulate you, and you actually, you do very well. Because many of the people don't know what they don't know. So you know what they don't know, and it's very good. Last but not least, next class will be presentation and quiz. Yeah, that will be the case. And if we still have time, probably we can go over the sample question. But I'm not sure we have time. But if we do over that. Or we have some review Q&A time if you want to ask. But of course, it's optional. You can extend that line already. Not yet do homework. Yeah, extended already. Paying slide means that only maybe appear in the quiz, but exam is not. Okay, exam is just focused on, I guess the thing is not in the pink area. Okay. And how long to present each group? I think already said how long you present. The presentation, you look at the order there. Final here, tell you the time limit of your group. Okay. Every member would have 2 minutes to present. You can have only one guy to present. That's okay. But that if you have one person group, you have a 3 minute, but otherwise a 2 minute. Okay. So something you may want to present. The reason why you want to present is I will ask who may be the best presenter. So you may get extra credit if you present well. Okay. But otherwise it will be that would be the thing. Okay. So that would be the idea. Okay. So try to do within limit, because we want to all go home on time, right? So that is the and next class, beside presentation and quiz, and also we have CTE. So that would be someone will come to do CTE. So cost evaluation. So sleep, I think so sleepy, I guess. Do we include prediction in the project? Up to you. It really depends on what's the goal of your study. You want to do a correlation study, or you want to do prediction? Okay. So, and these two cases depends on your use cases. Okay. You can do both. You can do either of them. Easy project, easy quiz, easy exam, and A. Easy project I cannot control, because you decide how difficult you're doing, right? Easy quiz I think is already very easy already. I think most of you get full marks, so I don't know how easy you want already. Very easy. You cannot get more than full marks, right? And exam you can check. It's not very difficult. And usually you look at the exam, it's like we're by module. Many people get 90 something more, and some people get 70. On average, it's 80 something. Okay, so that would be usually I've seen in the master level. So it's very by module. Okay. Exam rule is only hard copy. You can bring calculator. Okay. If you want, but I don't think I have any calculation. Well, probably not. Shouldn't be. Let me check my. The last question may need to do some division, but this question we will just do some multiplication addition. I mean, you can use hand to calculate, but you can bring calculator if you are super nervous about it. Here is it all the categorical data. You need to do recording. I guess yes, because you have to decide 1 or 0, right? Otherwise, how can you run regression? If that is, I think that is what you meant. I mean, of course, you have to change to 0, 1. Exam scope will be up to today's end of the day. So what we cover in the class, we cover. We didn't say, then it is not. Okay. And someone asked me why this case, because some of you notice because of when you do the assignment, they're missing data in the rating. So if you drop the rating, drop NA, then you will have no problem. You can drop NA or fill NA, or fill thing is also fine. But because I didn't say anything, you can do whatever you like. Right? So whatever thing you would be fine. Yeah. Everything has beginning, has an end. So but the beginning, the end of my talk will be beginning of your talk, right? So we'll be happy. I'll be just sitting here very happy. Eating, sitting there, eating peanuts and then nuts and happy. I will share peanuts with you guys, don't worry. Yes, this is not, we'll have lesson 7 and that's it. 8 or 9 or 10, I'm sorry, I can't cover it. As I told you, I spent several weeks in the summer to want to cover this more complicated material, but maybe too ambitious. Cancel the quiz. I think we should skip quiz because everyone get full marks already, right? So it's good to have some differentiation, hopefully. Not everyone get full marks, then probably I make it too easy. So the question is, after LISO, we get the important variable. And then how should we construct? Well, remember, LISO, once you're done, you're over, right? Because you go to prediction, right? If you want to do prediction, you do LISO, and the LISO is done to pick the best LISO, then that is your model, and you're done, right? And of course, some of you may ask, can LISO be used in other contexts? Yes, right? Because once you're done, when you have regression, have a lot of regressor, LISO can help us to narrow down what might be important, and you can check what can be dropped, and can actually helpful for you to do correlation analysis, right? Because LISO is kind of machine learning, right? The machine can learn what regressor important, what not, and then you can check if they're not important. You can drop by yourself, right? You say assignment deadline is 21st. I think the day after the exam, I guess, right? I make it, yeah, the day after the exam. So you can work on it after the exam. Okay. Still, if you have a one day and 1 night to do it. Good. So far, so good. Oh, it's me. Okay. Exam scope. I said already up to today's. At least up to lesson 6 and then lesson 7. I'll see what I can cover. Simple or better, the YY head. LISO is powerful. Yeah, I think I haven't covered that, but it will be there. Yeah, I think you got all right. Okay, with a bell shape here, that's good. And it's okay. Not that bad. Oh, the first time I saw this style, it's not increasing, it's increasing and decreasing. Interesting. And will be final exam easier than the sample? I think will be more or less the same level. Maybe the multiple choice is too easy, as some of you suggesting. I would try to make it a similar level, but when you need to submit a group project, I think I write down there when I do it. I think I'll write that down, right? But remember, I think you are just allowed to use 1 or 2 pages per person, right? So the projects, you only allow one side of A4 paper, right? So you have, so you just use 1 page, right? If you want guy. Okay. I said the written report will be on the last 22nd, 20th. Maybe give you 1 more day, maybe 21st, same time as assignment. Okay, maybe I give you a weekend. Okay, I give weekend. So maybe the 24th. Then I have time to grade because I do really need some time to grade. And I will make the project submission. So only one of you need to submit, okay? If you're in a group, just one to submit. No need to submit everyone, okay? Just one. Just only one guy submit, okay? Just one guy submit. To make it easy, I mean, I hope the member one submit so that I can check easily. Okay, just the member one submit your project. Okay, so sorry, I mean the member one submit the project. That's easy. Put it on the blackboard. So why you would be unhappy? So I just examine the thing I cover in the class. Okay, if not, then it's not. Okay? Now let's go to the lesson 7 is I think it's the most useful topic there. And onwards. I don't have time to cover everything there, but you can imagine this is the most important thing in business. The reason is because regression is just correlation, and prediction is just minimize the loss. But you really want to have a business decision. It's like I do X and I lead to Y, right? Suppose I have Airbnb or product feature. I want to implement this feature, and that lead to improvement in the profit or improvement in engagement of the customer and so on and so forth, satisfaction. So correlation or prediction cannot answer this problem. Okay, and we will do the causal analysis and random experiment. Okay, the idea is actually not new. You still run the regression. You still do everything you actually have done. But the thing is, you have to understand when the regression would imply causality. Okay, it's the same thing, but we just understand under what condition the regression we do will help us to say X lead to Y. Okay? Not X correlated Y or X predict Y. When you do X, you lead to Y changes. Okay, so that will be the key. Okay, so we have to define what is causal inference. Okay, what is the causal effect? What is selection bias? Okay, and then we will use one of the method we call control experiment, which is used often in the industry, accessory IT industry. They call it A/B testing. Okay, that was the idea. Okay, and there are many more techniques actually in the upcoming slides that we don't have time to cover. but you can check. But you will see to know causal analysis actually require a Ph.D. Indeed, many PhDs spend 5 years in grad school only to learn one thing, causal analysis. And they make their money just doing causal analysis. Okay, there are a lot of people doing that. If you know Amazon, it's a place they do a lot of this. And you look at the places that hire the most economists to do causal analysis, is Amazon again. Okay, I think they have more economists than Federal Reserve, and they are all doing this type of analysis. What costs what, and say change the price, change the feature, how they sell the product, how to improve the sales. Okay, and by doing this, they earn a lot of money. Okay, or Google or Yahoo, they do all of this. Okay, I'll tell you more story later, but let's quickly go into the detail. So don't worry, it's more a theory, more story, not much math. Okay, there's some math, but it's very simple math. Okay. So as we see, machine learning is good for prediction. Also, you learn the other cases. Lies is also good prediction. But the problem is when your prediction outside the data, you also fare very badly. And prediction based advice is very bad at doing what if. Okay. And very often we say high price predict high sales. Okay, you look at data, look at prices and sales. You imagine that high price lead to high sales. Okay, but if you think this is true, then you tell your boss, let's increase the price and we increase our profit, and probably you just fire immediately, right? Unless you are selling for designer bed, right? Otherwise, it will not going to work. Okay, why is the case? If you look at data, you're likely that high quality product or popular product are more expensive. Okay, and during the holidays, there are higher sales. Okay, so in holidays, this thing lead to this, very natural. Okay, if you don't know what is happening, you don't have holiday in your data, you don't have quality on data, this will fail badly. Remember the thing I mentioned, ice cream sales and shark attack. If your data only have these two numbers, you run prediction, you predict very well, right? And then probably you will tell your boss, okay, or the government, right, to avoid shark attack, let's kill the ice cream store, right? But it will be a poor product advice, right? Even you kill the ice cream store, the shark still attack, right? So you're out of job, right? If you have to advise the government, right? So that is the idea, right? You have to know what is behind the story. So that's the reason we have to do causal analysis, to understand what is actually behind your correlation. Okay. And machine learning is bad at doing this. Okay. And correlation alone is not enough. Okay. We understand what is a what if question. We have to understand what is counterfactual. Okay. Basically, you have to build a model. And important is we need to understand how the data is generated. Then you can ask the question of cause and effect, right? Just like why something caused ice cream sales and shark attack. It's because of the hot weather, right? So you have to understand what is it in your model? If not, then you make a mistake, right? That's why we try to understand how data generate and how they work, understand the background, okay? So that means that your domain knowledge is important, right? That's why you're a manager, you're here, right? Any junior guy or intern can run regression, right? But they don't know the background, right? You have to know the big picture. You tell them to run a regression, and then you understand. Then the regression will be meaningful. Right? So if the intern just tell you sharks attack and the ice cream, then you just say no. We have to understand the weather. You put the weather in the model, then everything can explain very well, right? Because once you run the regression, right, weather will explain the ice cream, and basically the weather thing, and actually people go to the beach and explain the shark attack, right? So that would be the idea behind. Okay. And as we said, correlation doesn't imply causality, right? And another example will be you go to the hospital, look at people there, people will be more sick than people outside hospital, right? So it's easy to conclude that the hospital make people sick, right? Which is ridiculous, right? But that is because of a selection effect, right? Actually, why people go to hospital is because they're sick, right? So that's why people in the hospital originally are more sick. But once they get into hospital, actually getting less sick than they are, right? So they are not comparing the same thing, right? It's not you're comparing orange to apple, so it's not the great thing, right? Another example is like this, right? The rooster, right? Scream every day in the morning, right? And then once it scream, and then the sun rise, right? And then if you look at the data, you would say, actually, the rooster caused the sunrise, right? I mean, every data is like this, right? Right? But it doesn't work, right? So, and another thing that is something new to you is causality doesn't imply correlation. This is something probably you haven't thought about it. Is X cause Y doesn't imply the data correlation, you will see X cause Y. Okay, that is something have to be careful. Okay, why is the case? Okay, for example, it's because I have many examples, but I will just use the first one. It's called human effect. Human optimizing. Okay. Okay. For example, you would think if you have high tax on cigarette, okay, of course, people would not spend that much money of cigarette, right? Because as an economist, right, it's more expensive. You would maybe try to drink more beer, right? Or you would smoke something else, right? So you would not say increase in tax in cigarette doesn't imply that you will see reduction in the smoking. Okay, you don't see the data. And why? One of the reason is they can go to Shenzhen and get a cigarette, right? Or get a cigarette from somewhere else, black market. Okay, so correlation doesn't imply by causality. Okay, and that is the reason why you can't really see it. Okay? There are many other reasons here. Not going to talk about that. Okay. So, okay. For example, there's another thing. Okay, I think that is you expect with AI, we are much more efficient, right? And we know that getting more efficient should increase our wages, right? Natural. Now, everyone with AI now, okay, we are much more efficient than last year, right? I think we're much more efficient than last year. Do we see our wage increase? Do you? I think my productivity increased by 50%, at least by 50%. My wages actually doesn't change, right? Why? It's because of everyone increased, right? So we just defeat the purpose, right? Everyone doesn't change a lot, right? I think there's a famous statement in the school is I'm now in China. What they said is 一个人的努力 ，OK， 就提高你的分数 ，OK， 大家一起努力的话，就直接提高分数线。So what does that mean? It's like if you work hard, okay, you improve your only one you work hard, you improve your grade. But if all your classmates work hard, you just improve the cutoff point for the A. Okay, you work hard, you get A, right? But if everyone work hard, you just make the cutoff for A higher. Okay, so if everyone don't study, right, the cutoff is very low, right? So that's the idea, right? So that means that causality doesn't imply correlation. Okay, so they're not the same thing, right? So that have to be very careful because you may not aware this imply that because it's clear that this doesn't imply this, right? But this doesn't imply this is not something that you will learn in the undergrad. Okay, and of course the question would be, we only know how to do regression, right? So the question is when this imply this. Okay, when this correlation imply causality? Well, that's a main question. And as I said, this is something that if people learn PhD, they would spend 5 years for that. Okay. But of course, that means that I only scratch the surface. I can't do too much about it. Okay. And we focus on one case is we look at only X. Okay. And how can you do this is look at the case where you have X, you don't have X, holding them constant, okay? And you change one thing at a time. Then you compare these two cases, then it must be causal effect. Okay, so that is the idea. Okay, so this idea I think date back to 1990, 200 years ago by some philosopher. They start with this definition. Okay, so IT, we have IT class. So imagine this case is I want to look at the new IT system. How can we have the causal analysis? Is you have the outcome when you have X and you don't have X. Another thing have to be unchanged. Okay. So the difficult part is this guy. Okay? But suppose you have this. Okay? You look at the difference. That is the causal effect. That's when the causal. Okay. Have to hold other thing constant. So that's how part. Okay? And as we said, we define the causal effect of X is you have it, you don't have it, it's stream minus control. Okay, so that is the fundamental question of causal analysis. That's what we define. See, have it and don't have it, and holding other thing constant. Okay, and regression is best for this purpose, holding other thing constant. Okay, and again, the problem in the what we call the fundamental problem of causal inference is something that is we can't do that in our life. Is you can't have a guy have X and don't have X at the same time. It's never possible. Okay. And either you have X and you don't have X at the same time, right? Either you have take the medicine or you don't. Okay, the patient, right? At least at the same time. Okay. So unless your time machine, you can do it. Otherwise, you don't, right? Because an individual, either you give him the new IT system or you don't. Okay? Either you give him the drugs or you don't. So that's why a causal analysis is a prediction exercise. Okay? Basically is the following, right? You have one of them, use the prediction. If you're this, you predict how it works. You have this, you predict how it works. Okay? And that will be our estimate of causality. Okay? That's a fundamental problem of causality. Okay? Is that okay? So basically is we have to predict. So you take the drugs, you recover. You have to predict what happens if you don't have drugs. Do we going to recover or not? Okay, of course, how you predict this is using other subjects similar and predict what's going on, right? If you don't take the drugs, you still recover. You want to see how fast you recover if you have taken a drug. Okay, how you do that? You're taking something similar to me, okay, and then also take the drug, and that's how you do the prediction. Okay, that is how what you do is you imagine what's a counterfactual. You imagine what will happen if you do other way around. And that's you can do causal analysis. You predict. Okay, you have a model to predict that. Okay, so that's why causal inference prediction problem. So that's why we can only talk about causal inference after you do the prediction. So let's quickly go over some notation. Okay, quickly. We have some people 1 up to n, and each guy we see what they do is y. So it's whether it's drug is how fast they recover, say. And 0 is not treated, and 1 is treated. So it's binary, not variable. So So consider with time machine, we have 4 individuals. These 2 don't take the drug, these 2 take, right? And this might be how well they're feeling, right? 5, 6, 8, 7. Okay. And to understand causality, there's a modeling framework in the 1960s, what we call the potential outcome framework, is assume, as we said, the guy who have 2 possible outcomes is yi1 is if he took the drug, this is the outcome. If he didn't, this is with 0. Okay. And the problem is we only see one of each, only one of them. Okay. We don't see the other. Okay. The other have to predict. Okay. If you see the one, it's called the observed one. If you don't see that one, it's called counterfactual or potential outcome. Okay. Okay. So if you write the formula here, is what you observe is coming from this formula. If you take the drug, this is 1. 1 minus 1 is 0. That's this guy. If you don't take the drug, this is 0. This 0, this guy. So this is what you observe. So this is called the potential outcome equation. It's called what you call switching equation. So that's actually this does mean this. Okay. If it take no drug, you will see the 1. If you take the drug, you see this guy. The problem is you're only able to see one of them. So that is the fundamental problem of causality. You're only able to see one thing. You don't see the other. Okay. That is very difficult, right? They're very difficult problem. Okay. Because the causality will be this minus this, right? But you can't see it, right? So consider with time machine, okay? If they don't take the drugs, this is how good they are. If take the drug, this is how good they will be. And actually they take, these 2 guys doesn't take the drug, the other guy does, okay? And because they don't take, you only see 5 and 6. If they take, that's why you only see 8 and 7. Okay, so this only observe, but this is potential is there, but you never observe this. Okay, so that's a fundamental problem. You only see this T and Y, but you never see Y, Y1. Okay, and here what we call the treatment effect is yi1 minus yi0, right? So it's a difference. But I have said to you before, you only have seen one of those. Okay, so this can never be understood. Okay, there's no way you can see it. Okay, so that's why we happen to talk the other one. Okay, and one thing that I have to remind you is different individual will have different treatment effect. Because maybe a guy who's more healthy, the drug may be more useful, so on and so forth. Right? Depends on maybe different gender, different thing and different thing. Okay. So here is the what we call the individual treatment effect, the last column. Okay. So you take this minus this is how -1. This minus this is 0 because taking the drug actually no changes. And this is 1, this is -1. Right? So this is the IT. Remember, this one can be different for each one. And this one can't be observed. But this in theory, this is something we want to figure that out. Okay, cannot be observed. Okay, so if I can't find this individual, what's the hope of doing this is we consider the average treatment effect, ATE. Okay, so there's something that you often look at. The people look at ATE, average treatment effect. So I can't find each one. So that's why I need to do many patients, ask them to take drugs. Okay, and look at the average effect of difference. Okay. And do you note that this AT can be positive, can be negative, also can be zero, because some people can be positive, can be negative, they cancel out, right? So here is too complicated thing that is slightly a little bit tricky. Okay. That is ATT and ATU. Okay. ATT is saying that, okay, looking at those who actually take the drug, okay, you compare they take the drug and before take the drug. Okay. And you also look at if they don't take the drug, what is the difference? So I will show you the example. Okay. ATE is just averaging all these four divided by 4. ATT will be just looking at those who actually treated. So see this last two column, the last two row, average of this divided by 2. ATU is just those who actually not treated. Okay. And why you care about this? Because I don't have time to cover it. But if you look at slides later, you will see very often we can discover that we want to discover this, but many times we can't. We only can do this. Okay, so there is some limitation, and sometimes we only interested in this. Okay, so but anyway, I don't have time to talk about this, but I'll introduce something very important, and then probably after this we shall have a break. Okay, very quickly. Maybe just this slide I have a break. Okay, I don't want to handle that. Okay, and the problem is we don't have time machine. So how can we figure out yi1 minus yi0, because we don't have that. We only see one of them. Okay. So if you look at data, right, or look at those who take the drugs, what's the outcome? And those who don't take the drugs, look at the outcome. Okay. What you will see is what we call the simple difference in mean. Okay. And you take this, then you will make a mistake. Okay. Okay. The reason is, in general, those who take the drugs and those who do not, it's not the same. You're comparing apple to orange. If you randomly assign people taking drugs or not taking drugs, that will be valid. But if not, you have what we call the selection bias. Okay. And the main thing about causal analysis is to try to remove this selection bias. And one of the important things, that's why in the internet or IT is what we call A/B testing, is randomly assign your subjects to different experiment. Okay, you will randomly say this guy will see my new IT system, the other guy is not, and as long as these two groups are comparable, and you randomly assign, when you run the regression, that's good. Okay, so imagine, but this is not easy to do it. But imagine that, right? You randomly put the drug to the patient, right? You randomly assign this, he has and he don't, right? Then that will be the effect. But if you're not, you cannot do this, then you're not. Okay. So, but telling you that if you try to look at the standard thing you think is natural, you make a mistake. Okay. So let's finish this slide. I'm done. Okay. I'm gonna have a break. So if you remember, without time machine, you don't have this number. Okay, because you only have 0 because you don't have treatment, and 1 you have this, right? So what is the case? Look at this, is average of this who take the drugs is 7.5. Average of those who didn't will be 5.5. The observed difference is 1, right? But you compare this drug is actually have no use, right? Or negative. So find positive is totally wrong. Okay, this drug is basically, if you know the number, it's actually bad drugs. Okay, actually make you bad. But if you look at only those who take the drugs, it's better, right? Because why? Look at data. Actually, those who take the drug actually are more healthy, right? If you look at data, right, this number are higher than this number. Okay, actually, it's like those who actually got treated take the drugs actually are more healthy, better than those who don't. Okay? So that's why by looking at the simple difference, you make a big mistake. Okay? And it's often the case. Okay, that's why have to be super careful when you look at the data. Okay, let's a break of 15 minutes and we come back and continue. I guess I don't want to bother you with the U reply. That should be fine. Có khả năng㗎.我諗緊會可能 M.Phil 啦。成分都唔怕嘅。唉，佢只係想大家都唔讀書咁嚟，分數低啲咯。大家都讀書咪即係提高 A 嘅分數線啫嘛。Combination 即係話佢用翻呢個就係當時單個 X 食嗰啲藥嘅，我淨係嗰啲，即係只係個條果，因為有時我食有少量，所以記住嗰個啫嘛。所以你永遠都唔知道佢，你知道你食得你呢個雙減即係你食入口。你食唔到我啫嘛，你食唔到我你咁所以另外一個嘢咯，你永遠都係靠估嚟。每一個人嘅係乜嚟㗎？係啦，冇錯。入翻佢冇食藥就個開心，食咗藥同4個開心，跟住有冇同都係定到成日開始講。呢個本身有睇書其他太水都係冇食入去得。你或者係睇佢收成，你睇唔到咁樣因為你係嘅個效果係4減5咯，咁你呢個條成都唔會你會見到你即係更加，跟住又講嘅，又收翻去我係俾你見唔到啊？你見即係見到㗎，你會見到㗎，你見唔到㗎？你真係見到，你見得好幾多嘅。你老實嘅你知啊嘛？咁呢個你見到佢行過，你見到啊嘛？咁呢個即係話俾你聽，佢係你見到晒所有嘢，
有上帝視角，喺上帝視角嘅，但係實際上我見到一嚿嘢，我會用個 model 入邊嗰啲嗰嚿嘢咯。你係咪左上帝嗰啲？你個 model 所以係咯，變一個喺度上，我識佢。所有我所謂拉咗嚟，呢個人見咗啊嘛，即係光就係呢個。你估下你好食係點咧？食得嘢好翻啦，你估下你唔食嘅，幾時翻咧？咁你要同你啲 friend 啊、你朋友啊計所以你翻嚟冇關係，第一嚿兩嚿。呢個就係開運嘅，所有波數人打嚟最主要都係做邊嘢？即平均地食咗藥，有咩？咁我哋點去？因為你記得咗你佢將錯晒，因為你除非你係 blender 有冇食藥，你咪想 compare 到㗎嘛？所以呢嗰啲人病呢個病死嘅人，你係要 compare 到。你要喺個去醫院嗰度嗰啲，係啦，嗰度真係就係 random 嘅出街。咁你個 compare 佢喺邊度嘅方式？係啦，呢啲就係有村民嗰班人，其實呢啲係呢個就係啱我哋你咁樣做係最基本上，即係你見到佢見到我嘅一部分你但係啲嘢喺度做係喺度，譬如話你咁樣明白。係有啲你永遠明明係醫院睇嗰班人醫嘅病啊嘅呢個。係啊，因為我哋睇你哋睇到佢有食藥嗰班人，你食翻，你又講翻係有頸症㗎啦。你又講食藥嗰班人係你成個車度的係好，即係我哋班有病嘅，佢一班人食有食冇食嘅，即係健康嘅食藥有病。係嗰隻咁樣搞嘅，所以你跟翻呢啲人係。你嘅翻呢啲，呢個都係。
So, can I continue my last 40 minutes? After that, you no longer hear me anymore. Then you exempt from my voice. You're welcome to watch anytime. Okay. So, someone asked me this question again. Let me give an analog. Okay. I think there's a study saying that married men or women are more happy they're not married. Okay. More than single. Does this mean you should get married? Does it get married get you more happy? The answer is no. But not necessarily. Because of it's possible that actually people are more optimistic getting married, right? Because if they don't get married, they may be even happier, right? So marriage can be negative. Who know what, right? But you never know, right? Unless you have some case, you force some people who get married, divorce, right? Or those people who won't want to get married, force them to get married. Then you can do, if you can do this, you know the effect of marriage. Okay. So same idea here, right? You can't really compare those who take the drugs and those who don't. This difference is not valid, okay? Because those who take the drugs, probably they don't have disease, maybe more healthier, okay? So when this is good is you have people who are also equally sick, okay? And you randomly say this group of people take the drugs, these people who don't, right? Holding out everything constant. Remember, have it and don't have it, holding out everything constant, then this difference is the effect. Okay, so that's why for A/B testing will only be meaningful only if you randomly allocate the treatment. Okay, and they are same, right? Then the comparison will be valid. Okay, and that is the type the slide don't cover is basically try to make sure that they're the same, and you take a difference you can compare. So let me say this, right? Because this is why this comparison is invalid, because remember in this example, actually those who take the drugs actually in this case are more healthier than those who don't, right? So that's why I spare you the math. Okay, just basically observed difference is the average treatment ATT, okay, plus the selection bias. Okay, and once you take away the selection bias, you discover the ATT. Okay, the average treatment on the treat. Okay, and once we're done, we're not done yet because we want to find ATE, right? Okay, but if okay, if your assignment of the treatment is the same, so ATT, AT are the same. Okay, if you think you randomly allocate the things, okay? The treatment is randomly allocated, right? Just like the patient are all equally sick, you randomly say who get the drug or not. Okay, then the treatment or not treatment is the same population, same thing. Then every treatment effect are the same, and this is done. Okay, so basically what we want to do is to make sure that whether you assign a treatment is random, and these two groups are very comparable, and then you compare X without X, then you get the causal effect. Okay. Okay, and you will see if you want to go further, I do recommend you to look at these two books. Okay, especially this book. This book is undergraduate, undergraduate level textbook. It's a very short, looks like a novel style book. You can read it without too much math. It's very easy. And this is more like the master PhD level. And Angus is a Nobel Prize winner, so I think this is economics. So probably you can, yeah. So you can try to look at this. It's very well written. And these books are more fundamental. You can just try to check those as well. So now I think once you know the SDO can be equal to ATT, ATE, those kind of thing, we talk about one way to make sure that happen. It's called experiment. Is you design how to test it. It's very IT manager often do it. Okay, so that's we'll give you the example of this. Okay, so we want to kill the selection bias. That means that we want to compare apple to apple, orange to orange. We don't want to compare apple to orange, right? Remember, as I said, if you try to compare the people in the hospital and outside, people in the hospital are more sick, right? But what you compare is compare people who before they go to hospital and after hospital. That may be doable, right? That can be the same guy before, after. It can be doable, but that will be, we call the different indifference, but we don't have time to cover that. But that's one way to do it. Okay, so we actually want to avoid why the reason why people take drugs or not. Okay, it should be random. Okay, we try to remove that. But by you are the guy who control it, controlled by the token and coin, rolling a die, or the computer decide who use the new system or old system. Okay, then you have no selection bias. Then the observed difference will be the causal effect. Okay, let me repeat. Is This is what you usually see, right? You take the drugs average, we don't, okay? And you want this to be meaningful. Actually, you do this actual regression, right? This actually, you run regression. CO1, this is a coefficient, right? This coefficient, you run regression. If a dummy variable, this is your regression coefficient, right? And the regression will be meaningful, okay? If you are able to avoid the selection bias, okay? As an IT manager, you can always implement that. If you randomly put your new website to a random visitor and see how they look at it, and just apply. Say Amazon, as I told you, Amazon has one of the largest group of economists, and they often different change different websites and different prices to extract more money from you. So a lot of time, you can run an experiment, but also the world is running an experiment, right? Like weather, sunspot, moon phase, or policy changes, right? So that can be done. Many things can be used as experiment. But very often we will do, as we said, we will do the free experiment, okay? Do some lab experiment, the lab asks people to do things, but I think in your IT manager, A/B testing is the thing that you often do, okay? So let's check it out, okay? So how to do A/B tests? The main thing is you randomize, okay? You would make your website or make your IT system adoption of new system, old system randomly assigned, okay? And that means that the potential outcome are the same for each group, okay? You can compare apple to apple, okay? You can't ask them to say whether you want to use the new system or old system. You cannot ask them. You have to tell them, based on lottery, okay? Based on your total coin. And then in that case, the selection bias will be 0, okay? You also can't choose, okay? And they also can't choose. Only the coin chose, okay? Then the bias is gone. So let's look at this, and this also appear in your sample question, okay? Is you have actually, very interesting is a social media website, and they put 2 versions of the ad for the master program. And this data is called A/B testing because they will say the following. One is called number 1 in Central Europe. The other is called top 50 in the world. I guess it's applied to CHK, right? We are top 50 in the world and number 1 in new territories. And which slogan is better? At least in the northern part of new territory. Or maybe best in Satin. That must be right. So so you want to send the ad to the master student, right? Then they click or not, right? So there are 2 things. One is there are 2 Y's here. One Y is whether they click, you send the ad, whether they click to the website. And also, after they click, at the end of the website, there's a form. You can fill in the email and the name, then can get back to you. So there are 2 Y's they can track. One is click, one is action. Okay? And the treatment will be, remember, is whether you have sold them, we are number 1 in Central Europe or we are top 50 in the world. Okay? And there's data from there. Okay? And there's data, download data from there. And the interesting part is, I don't know, suddenly the data become Excel. So that's why you use the PD read, not CSV Excel file. So, but there's nothing deep here. Okay. And you know the data, that is very simple data. Okay. That show you that I think they do how many 100,000 data for each, and under the A, which is I think is what's A? A is number 1 in Central Europe. Okay, we lead to this 2 number, and top 50 in the world is like this too. Okay, so let's do analysis. We want to do causal inference, right? So we have 2 million of data. Okay. So remember, because this is these numbers, okay, are coming from randomly shown ad. Okay. So look at the direct difference. It's already causal. Remember, because you're randomly letting people to see your ad either A or B. Okay. So that means that the difference between A and B is already causal. What does that mean? It means that your question. It means that if actually in this case seems like A is better than B in terms of action, right? So it means that you can recommend A, okay, and A is definitely a better choice, okay. But of course, not so fast, right? This is just a difference, okay. But is this difference significant? Need to look at the p-value, right? So just do the simple t-test, then we're done. Okay, do the t-test, right? Because you do the t-test to the difference, right? And then you can look at that, okay? And that's why I do it, okay? And you look at the book, they will tell you that, okay, I try to do something crazy. Instead of doing a t-test, I want to run the regression, okay? Because regression is actually a t-test, right? Remember regression. So, but it's not a data. That's why they create a data, okay? They fix the data and run the regression, okay? What they do is to create a data, okay? Column will be type A or type B, dummy variable, how many clicks, how many action, and you create 2 million data, right? Because 1 million for A, 1 for B. And then they will say the first 1 million data is type A, right? And the other one is type B. And then you create the data, okay, based on the clicks, right? From how many clicks you have is 1, right? Because they have clicks, then you create them 1, otherwise you call it 0. And same for there, okay? So basically they create some data, right? Based on this number because the clicks, okay? So what they're doing is, okay, from 0, okay, up to how many clicks they do, -1 because start from 0, okay? The clicks will set to 1, otherwise 0. Okay, basically they set first 3,323 are 1, and the rest are 0. Okay. And same for the B, right? From 1 million to 1 million, adding 3,128, right? They all 1, otherwise 0. Okay. So this is fixing the data. Okay. And once you do that, you can count, right? So this is exactly what you will see in the data, right? Bunch of 0, bunch of 1, right? So basically what they're doing is you create 2 million of data, okay? From the first data to 3,128 is 1, otherwise 0. For the clicks and action, same, okay? So once we do that, why I do that? Because I just wanted to do the t-test, but in terms of regression, okay? And what you're going to do is you run the clicks as y, how many clicks, whether you are type B or not, okay? And once you run the regression, the coefficient is positive, right? And you look at the p-value. The p-value is 1.5%, all right? So that means that is you reject the null hypothesis, they're the same. So that's why they're different. So the observed difference is yes, okay? So just to repeat what I said is, what I'm doing is actually these two numbers have difference, right? Is this difference big enough such that it's statistically significant, right? Is it due to the sampling mistake? No, okay, because the p-value is just only 1.5%. So it can't coming from sampling error, okay? It must be due to the actual difference. So we establish actually in terms of clicks, okay, A is better. Okay. And I would do the same for the action. Okay. Do the same. Okay. And you have that as well. Okay. And you run the same regression. Okay. And the p-value is 13%. Okay. So doesn't really make a difference in terms of clicking. Okay. Writing the answer, you just attract them, but doesn't change how much they leave the message. Okay. So that's what we found. Okay. So here is an analysis. Okay. So let's see this calculation. Okay. And this is the advertising expense. Okay. If you want to send an impression, ad is an impression, right? It will cost you like 0.1 cents. Okay. Per impression. Okay. I think it's a $1. If you have 1 million impression, you have to spend $1,000. Okay. I think in euro. They use in euro. In euro. So the data is you have this unique visitors and 55 the action. Okay. And you can calculate, okay, 30 per action, right? So you just divide this by the amount, right? This divided by this is this number, right? This divided by this is this number. Okay. So that means that B is more expensive than A in terms of action. Okay. Although A attract more clicks, but in order to get your information by email or the name, B is actually better, right? But of course, not significant, right? And you can calculate the percentage change in clicks and percentage difference in action. You just this over this and divided by the other way around. Okay. So the p-value is there, right? How you get these two number there? This 6.2 and 50 is just the difference, right? The p-value come from this number. Okay. So summary, okay. A has more click than B. Okay. And the p-value is small. So in terms of click, it's better. Okay. And A has more action, but it is not significant enough. Okay. So A has lower cost than B. Okay. But at least what is clear from here is at least you do A, right? So it's clear that you do A, but B is not. In terms of action, doesn't make it too much different, but at least A is a better one. Okay, is that clear? I think I'll swap, yeah. Because A is 31. Okay, sorry. The typo should be you should just swap these two numbers. Is that okay? And one thing I don't have time to mention is you ask why I want to run regression, right? You just this, why don't I do the t-test? Because in actual practice, you should include your data, run a regression. You should also include the characteristic of your data, the gender, the thing, because once you do that, you can improve your p-value, more accurate. So that's why I don't cover it here, but you would include ages and word gender, because although you do randomization, but happen to be some observable characteristic can be different. So it's better to control them. Okay, that's why you run the regression, even you do A/B testing. And next is, I want to talk about this very famous Bing experiment by Microsoft. Probably now, no, Bing is no longer exists anymore. Is it still exists? Oh, probably not, right? Still exists, okay. So it's very funny. Okay, consider the very interesting thing is A/B testing is in the search engine, right? This is a clickable line, and this is description. Okay, and I think one manager proposed that they don't use this one. Okay. Instead, they get the first line here. Okay, you can imagine that means shouldn't be any difference, right? Very similar, right? And same as the manager thing. That's why we make that. That's why they don't do. After that manager proposed it, they didn't do it for 6 months. Okay, after 6 months, nothing to do, then they do this. Okay, and they do A/B tests. Okay, what do you expect to see this one? Nothing happened, right? Just why would anything change? Okay, and turn out this is something super big. Okay, and this move the line upper. A/B testing tell you one thing: revenue increased by 12%. Okay, just move it up. Okay, because you can do A/B testing, right? Just some people will see A, some people will see B version. Okay, and what does that mean? It means that they earn 100 million more by just moving this up. Okay, and this actual experiment keep running many times around the world. Turn out this is more or less right. Okay, just move something is 10% more revenue increase. Okay, surprising, but this is one of the most famous A/B testing. Yes, it's famous business. You can look at Harvard business case. It's actually the real case. Oh, how do you understand this? Okay. Why? Why people want to click this? Because they're based on impression and click, right? Because you would see the first advertising, right? People scan this and probably don't read the first thing, right? You scan this, you see the same delivery, it's attractive, you just click it. Because people limit attention, they don't want to read the second line. But if you force them to read it, actually they would more likely to be attracted. Okay, so that happened. I mean, this is a very famous A/B testing. So you pick up whatever A/B testing book in business. This is the very first case, and people always talk about this. Is oh, this is the most wonderful thing A/B test. Okay. No, normal time. Normal time. I mean, flower, just example, is everything. So everything you go to the search engine, I guess you would. So actually you see that. See, actually imply, right? Actually have that. You also see this one here. The ad, the same, right? And everyone is doing this kind of stuff. Everyone. Hmm? This is not. This is not. So they are search engine optimized. If you do that, it's optimized. Okay. So this is not. You can see this is optimized, right? Actually, the same, even the same name, right? Same day delivery. Very famous, right? but this is not, right? This is not. Okay. Not everything is there, right? So this is not. Okay. But you can still see the first word here. Okay. So it's not something actually they implement it, even Google, right? Everyone implement it. Okay. You will see, you may ask why they do this, right? But have been shown increase the revenue by 10%. Okay. Consistently around the world. Okay. So you may wonder why, but that's happened. Is that okay? There's some question. I mean, you can go home to tell your boss if they haven't know it. Maybe you get a $1 million bonus, right? So, and one thing very important as well is when you do A/B testing IT manager, what we need to do is make sure that your changes doesn't change your experience metrics, right? Because can be very annoying if you just have many pop-up of the ad. Of course, it may be helpful in the short run, but in the long run, people will hate your website, right? If you keep doing this kind of bumping up the little window, right? And of course, it may actually help in the short run, but in the long run, people actually get out. So that's why it's so amazing, is because add a little bit word there doesn't actually worsen customer experience or not, right? And you don't feel much quantitative load, right? Don't feel your brain a little bit heavy after reading one more line, but you will not read another line, okay? If you go on a little further. Okay? So that's a little bit interesting, okay? And it's very famous. It's a very famous case if you want to talk about A/B testing. It's a single most important case. It's well known, okay? The Bing experiment, okay? And if you have nothing to do, okay, I do recommend you to read this book. This book is no math, okay? And the very first chapter we tell the A/B test, the famous A/B testing, okay? And very important because as an IT manager, it talk about how you would design A/B testing, right? Because in the example I have here, I have clicks and action, right? But in the real world, you have to decide what is your why, right? What should be the why that you should check, okay? And beside statistical significance, you should check economic significance, right? How big is the gain, right? And so on and so forth. There are many things that actually in this book is going to tell you. It's a very short book. I think it's like 200 pages, a short book, not very long. And I would also, you have nothing to do. I also recommend this book as well. And I mean, I don't know whether you want to learn anything, but if you have time, this is a book that very famous book that tell how a business case is how firms do experiment as a learning, okay, and learn how to improve, and this basically the statistics, A/B testing, okay, and that's how the learning, okay. And if you still have time, this is also a good book, but this is a little bit more advanced, okay. You can read this in this order. That's why I write in this order. Okay. And let me end our class and also our course with this poem. Okay. The role not taken. And this is often cited in all the causal analysis course. They will start with this one. Okay. Two roads diverge in a yellow wood. Okay. And sorry, I could not travel both. And be one traveler, long I stood, and looked down as far as I could to where it bent the undergrowth. So it means that you're looking at the two part of the role, either they're treated or non-treated, but you never know what's going on. You can look at it, okay, but you have to choose one of them, okay, and you're only able to guess what happened to the other one. You never know. You just think, right? So that would be the main idea behind the potential outcome, right? So one last thing would be the case is if your significant other, your wife, husband asks whether they ask you whether you regret getting together, you can tell them this story. I don't know, right? Why? Because I don't have potential outcome of the other case, right? I don't know what happened if we come together. So I can't say, right, whether this is the case. Okay. So I often ask my daughter whether I like her or love her, but that's my answer. I don't know whether if you are not my daughter, whether I love you or not, right? If you're not my daughter, I can judge. Okay. But it's a complicated problem I cannot say easily. Okay. So I guess I can end now, although I end earlier, but I think I overrun many times in the past. So I see you next week. Next week with quiz and your presentation.有啦，滿意嗎？Hopefully you are okay with it.